Hi everyone, and welcome to EET1021. This is the first part of lecture on chapter 18 of our textbook, and it will cover capacitive circuits. In this first lecture, we're going to cover the first four sections of the chapter, which are section 1. We will talk about the sine wave, and we will see that the capacitive voltage lags the capacitive current by 90 degrees. Section 2 of the chapter, we will cover capacitive reactance and resistance in series. Section 3, we will talk about impedance and the impedance triangle. And section 4, we will cover the RC phase shifted circuit. Okay, let's get started with the sine wave. The sine wave, and let's see how the capacitive voltage lags the capacitive current by 90 degrees. For any sine wave of applied voltage, the capacitor's charge and discharge current will lead the voltage by 90 degrees. Here is an example of a pure capacitive circuit. It's only the source and the capacitor. As we learned from the previous lecture, the way the capacitor will charge is by the current going back and forth, all right? On the positive side of the, when the voltage is positive, the current will charge the capacitor this way. On the negative side of the voltage, it will discharge this way and will charge this way, and keep doing that. Okay, therefore, when the voltage is at zero, right at zero, okay, either here or here, the voltage at zero has a current at its maximum value. As you can see right here, voltage is zero, the current is already at its maximum value. When the voltage goes to the positive maximum value, the current is already down to zero. Voltage goes back to zero, and the current is already at its maximum negative value, and when the voltage is at its maximum negative value, the current is already at zero, and so on. So in circuits that contain capacitors, remember that the voltage, the capacitive voltage, always lags the current by 90 degrees. Or we can also say that the current leads the voltage by 90 degrees. If we take the voltage as a reference, then the current phasor goes up and the angle is positive, so that means that the current is leading the voltage. If we take the current as a reference, then the angle is a negative 90 degrees, which we can say that the voltage lags the current by 90 degrees, or we can also say that the current leads the voltage by 90 degrees. So, and the 90 degrees phase angles result because the current in the capacitor depends on the rate of change of the voltage. Okay, it does not depend on the voltage itself, but in the rate of change of the voltage. This right here means the rate of change of the voltage, how the voltage changes with respect to time. So the 90 degrees phase between the voltage and the current is true in any sine wave AC circuit. For any capacitive reactance, its current and voltages are always 90 degrees out of phase. Now, they are out of phase, but the frequency must be the same. So we covered this in previous chapters. The frequency of the voltage, capacitive voltage, and the capacitive current, it must be the same, meaning that the same number of cycles per second must happen for the capacitor, for the voltage and the current. And the leading phase angle only addresses the voltage across the capacitor. The current is still the same in all parts of a series circuit. In a parallel circuit, the voltage across the generator and the capacitor are always the same, but both are 90 degrees out of phase with the current. Okay, so just like when we had purely resistive circuit, if we have circuits that have resistors in it and they're in series, remember the current is the same around the loop. So the current will be the same for every component of the series circuit. Okay, and also when we had resistors in parallel, we determined in the past that if we have resistors in parallel across the voltage, the voltage across all the resistors will be the same as the source. So the same principle applies when we have capacitors in series and capacitors in parallel. In series, the current is the same in all the components. In parallel, the voltage is the same in all the components. But always remember that the voltage and the current, they're always 90 degrees out of phase. So when a capacitor and a resistor are connected in series, the current is limited by both the capacitive reactance and the resistance. Remember when we defined the capacitive reactance in previous chapters? The reactance is the equivalent to the resistance in a resistor. They both represent opposition to current on the circuit. So it's resistance for the resistors, capacitive reactance for the capacitors. And each of the components on a series circuit will have a voltage drop across it, which will be for the resistance the same as the current times the resistor, just like we did before in the resistive circuit. And for the capacitor will be the current times the capacitive reactance. They both, reactance and resistors, they both represent opposition to current. So resistance times the current gives you voltage across a resistor. Capacitive reactance times the current will give you the voltage across the capacitor. So for any circuit combining capacitive reactance and resistance in series, the following points are true. So the current, it will be labeled just I, because if they're in series, remember, it's the same current that's going to go through all the series components of the circuit. So we can just say I for current instead of IC. The second thing will be that the voltage across the capacitive reactance or the capacitor, we will label it with a VC. And that can be considered as the same thing as the current times the capacitive reactance, or the IXC voltage drop. The same as we did with a resistor. To label the voltage across a resistor, we will say that VR, and that represents the current times the resistance, and that would be the IR voltage drop across the resistor. Keep in mind that the current I through the capacitive reactance must lead the voltage on the capacitor by 90 degrees, okay? Because this is the phase angle between the voltage and the current for a capacitor. Remember, that is something that we have to keep emphasize on, okay? The current always leads the voltage by 90 degrees in capacitors. Point number 4 will be that the current I through the resistor R, and it's current times the resistor, that would be the voltage drop on the resistor. And this voltage is always in phase with the current, because there is no reactance on resistors, okay? So even though the applied voltage may be a sine wave voltage, the alternating current in the resistance is always in phase with that applied voltage. In other words, the phase angle will be zero. They go through zero, and their maximums or minimums values at the same time. Basically, this list right here will be the same as the one that we just talked about. The voltage VC is 90 degrees out of phase with the current. The voltage VR and the current are always in phase. If the current is used as a reference, the capacitive voltage is 90 degrees out of phase with the capacitive, with the resistive voltage. In other words, we're using the current as a reference. We can always say that the voltage across the resistor is 90 degrees out of phase with the voltage across the capacitor. Okay, because remember that the resistor, the voltage across the resistor is in phase with the current and with the source. And the voltage across the capacitor is 90 degrees out of phase with the current. So if VR has the same phase as the current, so that implies that VR and VC are 90 degrees out of phase. In fact, the capacitive voltage always lags the capacitive, the resistive voltage. The voltage across the resistor lags the voltage across the voltage across the capacitor lags the voltage across the resistor by 90 degrees. Okay, for the same concept, the current leads the voltage in the capacitor by 90 degrees. If the current and the voltage on the resistor are in phase, that means that the voltage across the capacitor will lag the voltage across the resistor. And so when we combine voltage on the resistors and voltage on the capacitors, we can use the phasor triangle to calculate the total voltage. So when a voltage wave VR is combined with the voltage wave VC, the result is the voltage wave of the applied voltage VT. So out of phase waveforms may be added quickly by using their phasors. Add the tail of one phasor to the arrowhead of another and use the triangle, the angle to show the relative phase. Okay, so basically this is, hopefully you guys remember from your geometry or algebra classes from the past. This right here is the total voltage, okay? That would be, for example, the voltage on the resistor. This is the voltage on the capacitor. To calculate what voltage was applied to the circuit, well, we find the total voltage. And when we add two phasors, we cannot just add this one plus that one because that's not the way it is, okay? So we have to consider the angle, obviously, because we know that the angle will be 90 degrees. So what we need to find out is the distance from the tail of this one to the arrowhead of this one right here. So this distance right here will be the equivalent to the total voltage, okay? So hopefully you remember the Pythagorean theorem. Let me see if I can just go ahead and do some kind of explanation in here. Okay, remember from the previous classes that you had something like this, okay? This is a right triangle, and we say that this is A and this is B, and that would be C, which is called the hypotenuse. This is from I believe is Pythagorean theorem, okay? If you want to find out the value of C, you can say that C equals, actually it goes like that, C squared equals A squared plus B squared. So therefore C equals, if you take the square root on both sides, is A squared plus B squared. And that will give you the distance from this point to this point, okay? So we're going to apply the same concept when we work with phasors and capacitive voltage and resistors, okay? Now let's look at this example right here. In here we have here we go. And here we have this, for example, we have a circuit that has a resistor and also has a capacitor in it, okay? So on this one right here, this represents the voltage across the resistor, and it's 100 volts. This represents the voltage across the capacitor. That's 100 volts as well. However, we know that the resistors and the capacitors, when it comes to the voltage, they are 90 degrees out of phase, and the voltage lags the voltage on the capacitor lags the voltage on the resistor. So we need to find the distance from here to here, and we use Pythagorean theorem to get that. Here's another example, or the same one actually. You have this right here, the 100 volts for this, and 100 volts for this one. All we did was we moved this and put it on this side, okay? Now to calculate this right here, all you gotta do is take this measurement and say that will be 100 squared plus 100 squared. We take the square root of that, and that will give us 141 volts, and this will be the total voltage. So we can say that if we put a voltage from the source of 141 volts, the resistor is taking 100 volts and the capacitor is taking 100 volts. However, because these two are out of phase, so we cannot add just 100 plus 100. So we have to use this concept of basically the Pythagorean theorem to find the distance from here to here, and that would be the total voltage. All right, so here's another example right here. If we're going to use the voltage phasors, you use the resistors, and then the voltage on the capacitor is always lagging, so it's going to go down this way, okay? And this right here will be the total voltage. If we're using the resistance and the capacitive reactance, we'll do exactly the same thing. So if we need to find out what is the impedance of the circuit, we can add the resistance plus the capacitive reactance. When we add these two vectors, we're going to get this as a result, and that will be the total impedance of the circuit. Okay, so impedance again is the opposition to the current. Okay, so one type of opposition is called the resistance, the other type of opposition is called the reactance. So the combination of reactance and resistance is called the impedance. So impedance would be it represents the opposition to current. So as we mentioned before, in here we have a circuit that has resistors and also a capacitor. If we were to draw the sine wave across each one of these components, the current, because these two components are in series, so the current will be the same for both circuits, okay? I mean for both components around the circle. The source is a sine wave alternating voltage source. So if we were to analyze the resistor, we see that the blue line represents the current. So the current and the voltage, as you can see, they're in phase. Okay. they go through 0 and their peak value at the same time. 0 and peak value at the same time. 0 and peak value at the same time. So they all have the same phase. They must also have the same frequency. Okay? Now, analyzing the circuit, I mean the voltage and the current on the capacitor. Again, the current is in blue, the voltage is in red. Okay? This right here for the resistor, you see, they're on the same line. This is the vector for the current or phasor, and this is the phasor for the voltage. They're in phase. That means that no degree, 0 degree out of phase. In other words, they go in the same direction at the same time. Voltage and current on the capacitor, however, as you can see right here, they're 90 degree out of phase. Okay, because the voltage lags the current, so we say that the angle between them two is negative 90 degree if we measure from here down this way. So this is the current right here. As you can see, the current is always leading the voltage. The voltage is behind. See, when the current is at 0, this is as its negative value. When this is at its maximum, the voltage is at its 0. Now, when this one goes to 0, this one is at the maximum, and so on. Okay, so the voltage lags the current on the capacitor. And these are the sine wave representing those, the combination of the voltage and the current through each one of these elements. So, impedance. Impedance is also calculated through the impedance triangle, which, as I mentioned before, you can always adopt the concept of the Pythagorean theorem to find this impedance right here. So if you have a circuit that has a resistor of 100 ohms and the capacitor has a capacitive reactance of 100 ohms, so the total impedance on the circuit is not going to be 100 plus 100 because of the phase angle. Okay, so we have to measure from here to here, and that would be the sum of these two phasors. Okay, so when we do that, we must use the concept of the Pythagorean theorem to find this out. So the total impedance would be the square root of the resistance square plus the capacitive reactance square. Okay, so remember that adding phasors XC and R results in their total opposition in ohms, called impedance. As I mentioned before, the total opposition to the current in the circuit is called impedance. Okay, so if we have only resistors, it will be called the resistance. If we have only capacitors, it will be capacitive reactance. But in this case, because we have resistance and reactance, so we have to adopt a name, and that would be the impedance. Okay, the impedance is the equivalent to the total opposition of current in the circuit when we have resistors and capacitors, of course. So here's the same concept, okay, because they're 90 degrees out of phase, so we can use this concept of Pythagorean theorem to calculate the total impedance if we know the resistance and we know the capacitive reactance. Now, let me go back to this slide right here, okay? This angle right here, okay, this angle can be calculated by using the tangent of the angle, okay? So the phase angle with series reactance and resistors. So the angle between the applied voltage Vt and the series current I is the phase angle of the circuit. The phase angle may be calculated from the impedance triangle of a series RC circuit by the formula: the tangent of the angle equals minus the reactance divided by the resistor. Okay, and here is a clearer explanation. Okay, so we know that this is the resistance of the circuit by the resistor. Okay, and the reactance, capacitive reactance, is 40 ohms. So this will be the capacitive reactance. We know that they are 90 degrees out of phase, all right? So to calculate this right here, we will use Pythagorean theorem again. So the square root of r squared plus x squared, and that will be 30 squared plus 40 squared, and that will give you 50. This should be 50 ohms. Okay. So the current will be the total voltage 100 divided by the impedance of 50. That will give you 2 amperes. Okay, so now this angle right here is this right here, okay? So to calculate this angle, we take the tangent of the angle first. And remember, the tangent of every angle is the opposite divided by the adjacent. So that will be the tangent of theta will be, in this case, minus, because it's down, minus 100 divided by 100, and that will give you 45 degrees. Negative 45 degrees because it goes this way. This is where the minus come from, all right? Because of the voltage, this always lagging the resistor, so it's gonna be a negative value on the triangle, of course. And then you know, negative divided by positive will be negative. So you take the tangent of this angle should be equals to that. So to calculate the angle, all we have to do is take the inverse tangent of those values, and then we get the angle. Again, this right here should be a this should be ohms, okay, no watts. Okay, so let's see if we remember some of the trigonometry functions. Tangent trigonometry function, right? So if we have a triangle, an angle here, we have this triangle, right? It's a right triangle because this is a 90 degree right here. In this event, if this is the angle that we're talking about, to calculate the tangent of this angle, all we gotta do is divide the opposite divided by the adjacent. This side right here is adjacent to the angle, right? And this is opposite to the angle. So it's going to be the opposite divided by the adjacent. However, if we're taking this as a reference, this will be the zero line, and now this is below zero, so this should be a negative value. That's why we have a negative right here, okay? And then, you know, to find the angle, we take the inverse tangent on both sides, and now the inverse tangent of this division will give you the actual degrees of this angle. If we work in degrees, if you're working in radians, so we give you the radians in here, okay? Now, if we're taking this as a reference and this is leading, so so this, as you can see, this angle right here will go this way, so it's a positive angle. This one goes this way, is a negative angle. If I'm taking this as a reference, now it goes up like this, counterclockwise, so it's a positive angle. So again, to find the tangent of this angle, is going to be the opposite divided by the adjacent. Opposite divided by the adjacent. In this case, it's going to be positive, because if this is my reference and this value is going up, that means it's a positive value and a positive value. So the angle right here will be a positive angle. In here, this is a negative value because it goes down. If this is my reference, so this angle goes down this way, clockwise, that means it's a negative angle. That's why the negative right here, okay? And to find this angle, we take the inverse tangent of the opposite over the adjacent, and that will give us the angle. All right, let's take a look at this example right here. The phase angle of a series RC circuit. R for resistors, C for capacitors. Meaning that this circuit will have a capacitor and a resistor in it, right? The voltage source is providing a total voltage of 100 volts. Okay, the current is 2 amperes. The resistor has a resistance of 30 ohms. the capacitor has a capacitive reactance of 40 ohms. So in this case, we're going to find the phase angle between the current and the capacitor and the total voltage. Okay? Now the current in the capacitor, we know that the current and the voltage across the capacitor, we all know is 90 degrees. But now we're going to find the angle, okay, the angle between the current and the total voltage, okay? So remember, this current right here, the current is 90 degrees out of phase with the voltage across here, okay? Across the capacitor right here. Not necessarily across the voltage source, because we have a resistor here, okay? That's make an influence in the circuit as well. So to find the angle between the current and the total voltage, we need to first do this diagram, okay? If I take the current as a reference, I would say that the voltage on the capacitor lags the current by 90 degrees. So I need to find the total voltage right here. And we already know that this is 100, right? So, but now we need to find the angle right here. This is what we're really looking for. So from before, we know that the angle equals the tangent of this angle is going to be the opposite over the adjacent. So the actual angle is going to be the inverse tangent of that opposite over the adjacent, right? So in this case, if we're going to find this angle right here, all right, if we're going to find this angle, we can say that the theta, the angle, will be the inverse tangent of the opposite, which is this side, which is the same as that one, okay? In this case, would be the voltage across here would be this times 40, that would be 80, and divided by the adjacent, which would be this right here, which would be 2. Okay, so and that will give us the 53 degrees. Or we can also take the phasors for the instead of using the current and the capacitive voltage, we can use the resistance and the reactance. Okay, so the resistance is our reference. The reactance, remember, lags the resistance by 90 degrees. Okay, so to find this angle right here, we can say that the tangent of this angle is going to be this side, the opposite, divided by the adjacent. But this, as you can see, is going down, so it's going to be a negative value. So it's going to be negative 40 divided by 30, which would be negative 40 divided by 30. That would be the tangent of the angle. So to find the angle, we take the inverse tangent, okay, which will give us negative 53 degrees. So we can use this one, or we can use the current and the voltage across the capacitor, or we can use the resistance and the reactance. Okay, either way will lead us to 53 degrees. So now we can say that the total voltage right here lags the current by 53 degrees. Okay, before we talk about the voltage lagging the current by 90 degrees is true only when you have purely capacitive circuits. Now we have a resistor here that is influencing the total outcome. Okay, so these two are 90 degree out of phase. The current is the same across the around the circle. So this one right here, compared to the current, it is 53 degrees out of phase. All right. So now let's see what is the behavior of the angles, okay, between the total voltage and the current on a circuit that is an RC circuit, okay? R for resistor, C for capacitor. If the capacitive reactance on the capacitor is less than the resistor, then the angle between the current and the voltage source, the total voltage, is going to be a negative angle. When I say theta is less than 0 degrees, if it's less than 0, it has to be a negative angle, because it's going to be a negative angle somewhere between 0 and 45 degrees. Okay. Now, if the resistance on the resistor is equals to the reactance on the capacitor, in other words, an example would be if this is 100 ohms and this is 100 ohms, then we can say that these two, the current and the voltage and the total voltage, will be 45 degrees. The angle of the phase angle will be negative 45 degrees. Okay, negative because remember the voltage always lagging the current, so the angle goes down like this, clockwise. Okay, so if the reactance is less than the resistance, then the angle will be positive, but will be less than 45 degrees. If the reactance and the resistance are the same, then the phase angle between the current and the total voltage will be a negative 45 degree. And in the event when the reactance on the capacitor is greater than the resistance on the resistor, then the phase angle between the current and the total voltage is going to be, they're all negative angles. They're always out of phase by, these negative angles. However, this one will be more than, it will be less than negative 45. So it could be negative 53, negative 60, negative 70. Okay, it will be more negative. Okay, so this is the analysis when it comes to, if you want to analyze it using the resistance and the capacitive reactance. Okay, more resistance, the angle is smaller than 45, equals, then it's exactly 45 degree in the negative direction. And if the reactance is more than the resistance, then the angle is less than 45, negative 45. Okay. All right. Now let's see the concept of a RC phase shifter circuit. Basically, the output can be taken across R and C. That means the resistor and the capacitor, depending on the desired phase shift with respect to the voltage input. Remember that the voltage on the resistor always leads the total voltage by an amount depending on the values of the reactance in the resistor. So the voltage on the capacitor always lags the total voltage by an amount depending also on the reactance and the resistor. So if we go back over here, these are the values in which the voltage, the values that will determine, by how much the total voltage is going to lag the current. Okay. All right, let's see on this video right here, this part of the this circuit, I'm sorry. All right, this is the input. The input have 120 volts at the 60 hertz frequency. The capacitance of this capacitor is 0.05 microfarads. The capacitive reactance is 53 kilo ohms. Okay, the resistor, this is a variable resistor that can vary from 0 to 100 kilo ohms, and for this example we're going to set it for 50 kilo ohms. Okay, as you can see, the reactance is just a little more than the resistor. This is 53 and this is 50. And what happened? Do we get when the reactance is greater than the resistor? Then the phase angle between the current and the total voltage got to be less than negative 45 degrees. Okay, as we can see right here, if we take the voltage, okay, if we take the voltage as a reference, the voltage across the resistor and the voltage across the capacitor. Remember, these two are 90 degree out of phase, okay? And this lags the resistance, so it's going to go down this way. You can see right here, if I find the voltage of this across the resistor will be, it is the current times the resistor, right? So it will be 120 times 50 kilo ohms. No, not 100, I'm sorry. The voltage will be the current times the resistor, okay? So the current in here can be calculated by using the total impedance, calculating the impedance, and then divide that into the voltage, and that gives you the current. So you get the voltage across the resistor, get the voltage across the capacitor, and then you find the angle right here by finding this right here. Okay, so the tangent of this angle will be the voltage on the capacitor, negative value, divided by the voltage on the resistor. And then the inverse tangent of that will give you a negative 46.7 degree. So remember this, if this is greater than R, then the angle will be less than negative 45 degrees. In this case it is negative 46.7 degrees, so it is correct. Okay, this is the phase angle between the voltages. I mean between the voltage on the resistor and the total voltage, this voltage right here. So if you can see right here, 46 degree and negative 43.3, these together add up to 90 degrees, which is the same thing that we have here, okay? Okay, we're gonna stop right here. We're gonna stop in here because just to, not to make the video so short, I'm gonna come back with another video to cover the second part of this chapter. Until then,